Welcome to session 5 of the Maximum Likelihood lecture. In this session, I will pick up a couple of kind of odds and ends of things that we need to know to be able to apply and evaluate maximum likelihood. But we'll start out with a note regarding maximum simulated likelihood. There's one kind of caveat to understand. Other than that, it really is the same in its practical application as doing regular maximum likelihood. It's just that when you write your likelihood function, you code it, you need to embed a Monte Carlo simulation routine to get numeric estimates of the integrals. Other than that, it is going to be exactly the same. So there's not too much to say about it. But let me just briefly go over a couple of comments. You can see the paper in the readings on maximum simulated likelihood, and in the appendix of that paper, I also provide the proofs. If you're interested, they follow somewhat similar to the maximum likelihood proof, only now what I really show is that the maximum simulated likelihood is essentially the maximum likelihood plus a simulation error, which goes to zero asymptotically, leaving us with the same properties asymptotically as the maximum likelihood estimator. So our log likelihood function is the sum of the log of the probabilities across independent observations. And as we know from the Monte Carlo simulation lectures, that we have a simulated estimator of probabilities such that the expected value of that estimator is the probability. It's unbiased. But we're working with the log of probabilities, which is a nonlinear function of the probabilities, and therefore the noting that the expected value of a nonlinear function is not the same thing as that function at the expected value. We essentially have a biased estimate of the log probabilities. So our Monte Carlo simulation provides us with an unbiased estimate of the probabilities. It just doesn't give us an unbiased estimate of the log probabilities. What are the consequences of this? Well, again, even as we start in maximum likelihood, we're not generally known to be unbiased in general. So I guess that's not that great of a concern. The concern is, what does it do to our asymptotic properties? So it turns out that if R, which is the number of sample points you use to get the integrals, is fixed at any value, then the probability limit of the maximum simulated likelihood estimator is actually not the true value, which means that it is not a consistent estimator. If the number of samples rises along with the sample size itself of observations, then it is consistent. And if this Monte Carlo number of points rises faster than the square root of the sample size, it's also asymptotically efficient and asymptotically normal. So essentially what we're saying is that the arguments are based on the limits across two things, n and r, of the likelihood function. And here's where it gets tricky. Mathematically, we can make all of these statements above, and they make sense. In the applied world, well, where's the race, right? I mean, we aren't actually letting either the sample size or the number of Monte Carlo simulations go to infinity, and they're not going there with any rate at all. We just pick the numbers, right? Or we sample until we get a certain criteria and then we stop. So there isn't a race anyway. And where we can think of it in terms of asymptotics on one parameter is sort of making sense. It means that the larger we get, the better it is. Since this has to do a comparison with the rates of two different numbers, it gets to be a little strange to think of what do we mean. Let's suppose that I were to pick an R that was larger than the square root of my sample size. This is not the same thing as saying that it's going to rise faster than the square root of n itself is rising. So even picking larger r's than the square root of n does not have really anything to do with the property necessary to achieve these consistent results. So it's just an interesting conundrum where the mathematics makes sense. The application of them, though, is somewhat nonsensical. So the real question becomes, in pragmatic terms, what are the consequences? Well, really, it will turn out that if you have a sufficiently reasonably large size for R. And it can be, depending on how you do it, it can be in the order of a few hundred per integral. You'll be fine, and the results really won't be much different than they could be if you could run your race, so to speak, as n gets large. But technically speaking, the maximum simulated likelihood has its asymptotic properties tied to a mathematical idea that really is not clear how to implement in the applied world. We're just fortunate that when you do it, you can run Monte Carlo experiments and you can find out that it doesn't matter. I have a reasonable size R, and for my sample size, my estimates are actually recovering essentially the estimates that I'm interested in, and indeed they are becoming reasonably close to a normal that I can use the normal approximation for my confidence intervals and tests. But just a point to note is on once you get these more complicated estimators, the underlying mathematics tends to depart a little bit more from a real clear understanding in the applied sense. All right, now let's move on to the question of the finite sample issues of bias themselves. Right, this is true for either one of the simulated likelihood or the regular likelihood. So, if we're looking at the expected value of a statistic under the actual distribution as being the value plus some bias, so we have an unbiased estimator, then we say the bias is the expected value minus this theta. So we can estimate this by, strangely enough, by using our estimate as the actual value, and then using the empirical CDF to come up with the expected value of the theta hats. Plug those in and we will get an estimate of our bias. Right? So what does this mean? How do we, in the real key, this one is straightforward here, right? This is the maximum likelihood estimator. The question is what is this? Well, it's going to be a bootstrapped estimator, and it'll be the average of the bootstrapped estimates. What the bootstrap is doing is it is assuming that the histogram of the data constitute the distribution in the population, and so it will sample with the replacement from that pseudo population, which is to say from the data, to create samples. It will run the estimates, and it will get the maximum likelihood estimate for a sample, and it will repeat this as many times as you want. So you may want to bootstrap 100 samples, so you will then, let's say your sample size is 500, you will go in and bootstrap 500 observations from the data set, run your estimate, so I will get 500 data points, I will get a theta hat 1, this is all from the actual data. I will then do it again and get a bunch of data and get another theta hat 2, and I will just keep repeating this until I get however many estimates I'm going to bootstrap over and over again. This will give some distribution of estimates, right? And so now I can get the expected value of those parameters, and that's going to be the theta bar BS over here. So I can take that average and subtract it from the actual estimate that I got on the real data, and that gives me bias, an estimate of the bias, right? So now I can have my theta corrected as the maximum likelihood estimator minus this bias, which really, if you do the algebra, simply means that I take 2 times my estimator and subtract the average of the bootstrap sample. Now the problem with this is this is going to be bias corrected estimator, but it has a larger variance. So it's a bit of a trade-off there. Now, the same thing we can look at using Bootstrap to estimate our variances. So the variance is the variance of our statistic under the distribution F, and I can have a bootstrapped estimate of the variance by looking at the variance of the maximum likelihood statistic based on the empirical distribution, which is to say the data itself. And again, what that means is I have got a true population distribution. I have a sample, and I assume that the sample is providing me a good estimate in terms of its distribution, as if it were a population. So now I'm going to sample from this sample to get a bootstrap set of data from which I will get a theta, and I will bootstrap again to get another sample, which will vary by sampling, and I'll get another theta hat. From all of these theta hats, I get a distribution of the theta hats, right? So the variance is going to be the variance of this distribution. So here is the population from which I got my actual data, from which I bootstrap samples all the way down, from which I get a set of estimates. All of those estimates give me a distribution of the bootstrap sample estimates, and I can get a variance. So that is the bootstrapped variance. Okay, and this is going to be helpful later on in our work to be able to use this. This whole technique of bootstrapping, actually, to get this distribution, even if we're not going to use the variance, will be very helpful, because this distribution is a reflection of the sampling distribution of theta hat, and we can use this distribution to ask questions of whether we've converged to a normal or not. So this will be helpful. But then if you want a bootstrap variance estimator, you can just take the variance of that sample, that bootstrap sampling distribution. You can use then this information to create bootstrap confidence intervals. You can use a semi-parametric approach, which is to say that you can simply use the bootstrap variance standard deviation as your standard error, and use that embedded in the presumed distribution of a normality. You can also, if you're not happy with the idea that the underlying distribution is normal, it hasn't converged, it is asymptotic, remember, and it hasn't converged to normal. And when all else fails, you can use the distribution, which is to say my sampling distribution, which I had right here. Let me redraw that, of the bootstrapped estimates. And I can just pick out the confidence interval according to the to say you want a 95% confidence interval. You've got the theta hat lower associated with the 0.025 percentile, or you can, and then use the upper for the 0.975, and this becomes a purely non-parametric confidence interval based on the distribution of the bootstrapped estimator. And so this can be very helpful if you're not at all confident in the distribution of the parameters. You can do a bootstrapped distribution and then use this percentile. This will tend to be wider than other types of bootstrapped intervals that you can use. A little more conservative that way. There's also some other types of estimators that can be a little bit of a bias-corrected accelerated estimator. Stata has that in its abilities. In fact, it's got a number of different bootstrapped estimators, and you can look those up and see how they do the particular nuances between different bootstrapped estimators in terms of confidence intervals. All right, so now that we have all of this, let's move on to the question of how do we pragmatically work with these maximum likelihood estimators. And in fact, this also will apply in many respects to the rest of the course, nonlinear least squares, generalized method moments, etc. And this is when you're estimating nonlinear functions. If you go back to the discussion in the lectures on optimization in Monte Carlo, you can become suspicious that the results may not be good results, given all the caveats that are involved. So the real question is how do we check the solution that our theta hat is actually a good one, and how do we check the distribution so that we can make good judgments in terms of confidence intervals and tests. And then we talked about how to use Bootstrap if it is necessary, how to do that. So one question is it quadratic around the solution? Right, now this is the question of whether you've got a good solution and how you're going to use it um, for, for your inference results. So one way to do this is you could plot the objective function around the solution. Right? So you can create um, a set of points, beta star, that is essentially your estimate, beta, and then go a certain number of standard deviations that I have from beta hat. It really doesn't have to be a standard deviation. Really what I want to do is here's beta hat, and I'm going to look in this area from here to here. And one way to do it is specify it as a certain number of standard deviations away. Is one possibility. That's fine. So you set up a set of values, -2, -1.9, all the way up to 2. Usually you make it symmetric, so it goes the same distance on both sides. And I want to essentially get a big magnifying glass, and I want to look at the objective function in this range. Right? So I can calculate this objective function for each of these points, and I can plot it. Right? And I can ask, is this quadratic? Right, that becomes necessary for the usual standard error estimators that Stata is going to provide. It can also be useful in that you want it to be quadratic as an indicator that you are in a proper solution for the different algorithms that you're using, as opposed to it just going up as a slope or whatever, and you've stopped it, or it's just not conversion reported a value. Stata will not, fortunately with Stata, it will tell you if that were the case. That's not quite as much of a problem. So we can look at this, but it's sometimes difficult to know whether that's quadratic or not just by eyeballing it, just because it looks like a hill. So one possibility is to transform it to linearity. So when we're looking at maximum likelihood, you can create a quantity for each of those beta stars that you did as the sine of the beta star minus the beta hat times the square root of 2 times the log likelihood of beta hat minus the log likelihood of beta star. You can, I'll say this now because it will apply to next week's lecture. You can do the same thing with the sum of squared errors for the least squared estimators. You take the sine of the difference and you look at the sum of squared errors. In this case, it's now beta star minus that of beta hat. And in this case, you want to divide it by the variance. But you use this quantity. And now if you were to plot this against beta star, it should be linear. You could also create another variable, which is beta star minus beta hat divided by its standard error, and plot this tau, which is up here, with respect to the delta. And now it's not only supposed to be linear, but it should have a slope of 1. All right, so you can graph it, but you could also now use a regression to identify the slope of 1. I'm saying you can regress the t on that and look at the slope as 1. Another possibility is to look at the profile likelihood. And the way you do this is that you are not going to just above essentially what we did is we took the likelihood and we took a cross section along the dimension of our estimator and said, what does this look like? Right. Well, profile likelihood is going to be a little bit different. The profile likelihood, you are going to get this profile estimation of the set of other parameters you're not investigating associated with the specific parameter value that you're going to look at. So you again come up with, now I'll call them theta stars, and they will be the set of values on either side of theta star. You will fix that parameter to one of the values in theta star. You will do a constrained maximum likelihood to estimate the etas, the rest of them, and then you will save that likelihood value. Right? Then you will do that for all of the theta stars. And then again, you can plot the this profile likelihood versus theta star, or you can plot the tau and the delta again. Right? So in doing that, your profile likelihood is maximizing over the parameters that you're not fixing, and you get this kind of following difference. The profile likelihood is going to do this kind of a slice here, pretty much, for this type of a curve, whereas the first option I showed you is just going to look along this parameter value, and it's going to go a straight slice this way. And that's the difference. In terms of evaluating the quadratic nature of the hilltop, I really don't see the pragmatic difference between the two. In fact, in some ways, I just like to take the slice because I'm trying to estimate theta hat, so I want to look at how is it shaped along that dimension. Profile likelihood actually is going to become a useful strategy, not only just to look at the shape of the hill, but actually as a strategy for getting estimates of parameters theta that when you're not interested in the other parameters eta, as I used in above. So it's kind of a way to account for what are called ancillary parameters. They're parameters in the model, but you're not interested in them. But as far as looking for the shape, you could go either way. You want to consider, what they, whether it's quadratic at the top. Typically, the log likelihood is more curved than the profile likelihood. All right. Now, what about an analysis of the specification of the model itself? Well, you can look at residuals. And residuals should show no discernible pattern, with one caveat. I should say it should show no discernible pattern other than what is expected given the model. There are, so for example, if you were to do a gamma distribution, then the variance is a function of the mean, which means the actual residuals being the y minus the predicted value or the predicted mean, and you were to plot them, you would actually expect the residuals to be heteroscedastic in similar accordance to the fact that the variance is a function of the mean, right? So if I were to plot the residuals with y hat, which is the mean, I would expect the residuals to have a gamma shape where it's getting larger variance as the mean goes up, because the variance is in fact a function of the mean, right? So I guess when I say no discernible pattern, what I really mean is no discernible unexpected pattern. You use this fact to help actually assess whether it is a gamma, right? Because if it is a gamma distribution, then the variance should be a function of the mean. Therefore, the residuals should actually be heteroscedastic in a very specific way. So what kind of residuals do we look at? Well, the residuals that I was just speaking about here are the mean residuals. They are kind of what some call the raw residuals, and they are the value, the observed value of y minus the estimated expected value of y hat, predicted value. There are also Pearson residuals, and that's essentially taking the raw residuals and standardizing them. And so that's going to divide by the, typically actually, let me go this way, there we go, by the standard deviation here. So the variance is the variance of y given x. And for the maximum likelihood estimator, there is also the deviance residual, which is the sign of the difference between it's basically the sign of the raw residual, times 2 times the log likelihood at theta hat minus 2 times the log likelihood at theta hat and y and x. And these residuals can be standardized. And if those are not enough for you, there are lots of other residuals for very particular cases, right? So if you're going to use generalized linear models, they have certain kinds of residuals. So the real key is that residuals will be very helpful to evaluate your model, and which residuals you use would depend on what kind of evaluation you're doing and what kind of a estimator that you're using. I like to look at these residuals as a minimum, because these residuals I have the ability to assess just fundamentally whether the function is doing what it should do, just as I said with the gamma distribution, right? Or if it's supposed to be homoscedastic and it's supposed to be the variance is not a function of the mean, then it should, in fact, the residuals should be just pretty much homoscedastically related to, mean of 0 and just randomly around the 0. If it's supposed to be a function of the mean in a certain way, then I should be able to see that. So I actually like using these as a starting point, regardless of what other residuals that I want to do. The Pearson residuals can be a way to identify if your variance function is proper, because if you divide by the estimated standard deviation and it is proper, then you should end up with a homoscedastic distribution of the Pearson residuals. And then the other types of residuals are very helpful for very specific purposes, and I would refer you to the estimator that you're using, that literature. And probably the easiest way to do this is to look through the available residuals and residual analysis in the software that you're using. Right? So if you're using Stata for any of your commands will have a certain number of residuals available to you. Look up in the Stata manual, they will tell you what they are, and essentially a good guide to start understanding how to use them. So rather than try to go through all of the individual details, I simply state you need to understand the different ways to evaluate residuals and the different residuals. We will focus really on these two in this class because they're kind of generic. You could look at these across all the different estimation techniques and get some information out of them. That is not to downplay the importance of other types of residuals. It's just that they're more general across the different kinds of models we're using. So for class, we'll focus on these. And I will simply say, for any estimator, go find the other types of residuals that can give you information and take advantage of those. As we know, I'll just state this because you've already had your regression courses, that of course the sum of squared residuals can be an index of fit, not necessarily a great one depending on what you're using, but it can give you an index of fit. The different plots, you can use the residuals to plot them, right? You can plot the residuals versus the observation number, just to identify who's sticking way out, who's far away from the crowd, so to speak, in terms of their residuals, their deviation in one sense or another. You can plot the residuals with respect to x, it's a misspecification of included variables. In other words, did you actually get the mean function properly specified, or the skedastic function properly specified? This can help you understand if it was specified properly with whatever variables that you're conditioned on. You actually can plot the residuals with respect to other variables. Now, technically, this is not about specification of the distribution, because if you're looking at the distribution of y given x, then there is no role for z in that at all. It's more of a question of if there's a relationship between the residuals and z, then it might be an indication for that model's use to identify parameters of an underlying structural model that you have excluded variables. And here you want to keep in mind the difference between the misspecification of a statistical model as it relates to a structural model being different from the misspecification of the distribution in its own right. Right? The expected value of the distribution of y given x is a distribution. There is no such thing as a confounding or excluded variables because you are trying to figure out what the distribution of y given x is in its own right. So in that sense, excluded variables don't exist. They only are considered excluded if they are essential for the identification of your parameters with an underlying structural model, and that's where this can help out. You can look at the plots with respect to various statistics. So you can look at the plot of the residuals with respect to the linear combination of x betas, assuming that you have such a linear combination in your model. You can look at it with respect to y hat. This one is extremely common, very good to use. And other such statistics if you want. You can also plot r squared with respect to different values, and the reason for that is to get a sense of how the variation in the conditional variation is a function of other variables. So there's a number of plots based on residuals that can be helpful. And again, your software will give you what they can do automatically, and if not, then you have to program it yourself. But if they have it automatically in your software, they'll probably in their guide give you some sense as to the utility of them and how to use them. Now, for those models that should have residuals that are normal, then you can evaluate that by looking at what's called a p-norm plot and a q-norm plot. And here I've written out what they actually are. I won't worry so much talking about that because these are very standard, and you should look up in, well, what I'm calling p-norm, you look up in Stata for p-norm and q-norm, and it will give you these equations. They're fairly straightforward. It's to say that if, in fact, the residuals are normal, these plots of these terms should be linear. You will notice if you plot both of them, they do slightly different things. The p-norm emphasizes the normal more, so it really focuses on whether emphasizes the middle more. It really focuses on whether, it's fitting well in the middle as a normal would, and the q-norm is really kind of highlighting the tails. You can think of it as it's really sensitive to departures in the tails. Good or bad, right? So if it's really sensitive to departures in the tails, then maybe just the plot, you don't want to overemphasize if it's off on the tails because it's going to really pretend that it is. And in other ways, if you're really concerned about the tails, then you could say, well, this one's going to really focus in on it, and perhaps I want to be careful not to use a normal if there's problems showing up here. So whether these are pointing to problems or not depends on the nature of your analysis. All right. Let me just leave this. This is just simply showing a distribution and how it looks under different parameterizations. The reason for that is that if the parameterizations are not different parameter values, with a beta, if conditional distributions span a lot of these different types of forms with different x values, then be aware that your residuals will reflect that, because once you or the raw residuals will, because once you subtract out the mean, you still get the basic shape, and the shapes could be different for different x values. So in really complex type distributions, you have to be careful about how you interpret the distribution of residuals. Now, in addition to looking at graphs, there are some more formal tests, and you can look at tests regarding nested models. And really what this is to say different specifications typically of the set of regressors. And you can do likelihood, Wald, and score tests. These are the three classic tests. We'll talk more about that in a little bit. You can use the deviance, as we had mentioned above, the -2 times the log likelihood of theta minus the log likelihood of theta hat. And since you're going to compare two models, trying to compare models, then what you end up with is actually the -2 of the log likelihood of theta 2 hat minus theta 1. In other words, the two different models. And you come down to a quantity here that is essentially the deviance of the first minus the deviance of the second with a constant added to it. And this particular statistic has this one up here will have a chi-squared distribution. And if you look at this one down here, you will have a chi-squared p minus r distribution. So slightly different in the different forms of what you're looking for. One is if you're just analyzing your model, and one of this is if you are comparing your models. Now, if your models are non-nested, then you can use a number of tests that are designed for non-nested models. So for regression, you've got what's called the PE test. You can see the green book for that and the readings for that. You can do what's called a J-test. And you can use what's called a Vong test. And these are all essentially comparing the results under the two different models, right? So in this case, you create in the Vong test, for example, you create a variable that's the log of the ratio of the density values under the two models. You create another variable that is the mean of that across your sample, standard error, and it's asymptotically normal 0, 1, so you could base a test on this. The expected value of this term is equal to 0 if they're equal to each other. So you can test it, or you can just simply use a criteria. Here's the suggested criteria, and that is if the absolute value of v is less than or equal to 2, then really neither model is favored. If it's greater than 1, then it's greater than 2, you go to model 1. If it's less than negative 2, you go to model 2. If there are a different number of parameters in the models, then you make an adjustment. Here's the adjustment, the log of the sample size over 2 times the difference in the number of parameters in the models. A similar type one, and this is one that I actually like and will have you do in homework, is Clark's sign test. And it is based on a statistic that is P2, the number of parameters divided by 2, the log likelihood of the first model minus the parameters over 2, the log likelihood of the second model. And it is using a paired sign test for this. So essentially you're looking at, and what this is doing, and the Vong test as well, is essentially saying if these two models are equally representative, they're both equally good as models, then ignoring for the moment these concerns about different parameters, the basic idea is if I were to randomly sample an observation out there, I'm not exactly sure what's going on here. If I am to randomly sample an observation, I would expect that they would just by random chance, 50-50 chance, one would be better than the other, right? And so this will be based on the concept that the differences being positive or negative has a 50-50 chance. And that's how it's going to create the test. So it is essentially a sign test, a paired sign test more specifically, of these differences. Another strategy other than testing is to use different model selection criteria. All right, so there's the Akiaki Information Criteria, AIC. And I won't get into the details of how it's calculated. You can look that up. It is based on minimizing the Kullback-Leibler distance, pseudo-distance, I guess, better way to put it. And asymptotically, it's the same as a cross-validation method. There is also, and what this is doing is it's saying that you want to pick the model that has the smallest number for AIC. And BIC is slightly different definition. Right, this is -2, the sum of the log likelihoods, plus 2 times the number of parameters. And this is negative 2, the sum of log likelihoods, plus the number of parameters log n, the number of sample size. And so you could pick the smallest BIC as your favorite model. You can do cross-validation methods where you randomly split your data and run estimates of the models on both to make a determination as to which one has a better overall fit to the data across samples. You could, instead of randomly split for cross-validation, in which you randomly split the model, you fit the model into one. Let's put it this way. Here's your actual data. Seem to be running out of the ability to do this. Here's your actual data. And you randomly split into 2 groups. And you estimate on this one, and then you predict on this one. And the model that does the best out-of-sample prediction is the one that you would favor. Right? So you can look at mean squared prediction error, absolute prediction error, and you can do this by resampling over and over again and then take the expected mean squared prediction error and use that as a way of considering the different models. Okay, that's what I mean here is the mean squared predicted error. If you were to look up the Journal of Mathematical Psychology 2044-1, that whole issue is on selection criteria. It is an excellent kind of course in many nuances of selection criteria. What I would recommend that you consider, though, is that selection criteria are about, even though the AIC and BIC have asymptotic arguments with respect to what they mean in terms of the statistics themselves, they are in practice used as a number. And you would say that this is the better model, that's the better model, because it is has the lower values. It's not a statistical test, right, in using them as a criteria. And consequently, Model 2 might have a better AIC than Model 1, but if you were to actually test that difference statistically, you might just as well say, well, they're no different. In other words, the data can't tell you statistically that it couldn't be Model 1 and you just got the data that favored Model 2. So one of the concerns about using criteria in that kind of raw form of which one has the better number is that you're discounting the whole data generating process and its uncertainty. And you're simply going for the model with the best number when in fact it really is not statistically has the evidence that it's really better than the next best model. And if those two models give you different inferences about your substantive question, you probably don't want to bet on it just because it had the better AIC or BIC or particular criteria. So one of the issues with using criteria is that it doesn't account for the sampling variability, and that's important if you're going to use the data as evidence that it should be one model versus the other. So it's a tool, but I would caution not to weigh too heavily on it alone. So this ends this particular session, and you can go on to the next session to understand some of the other types of tests that we use in estimation.